Hey there. This is the lecture for section 7.3, double angle identities. All right, in the last section, we looked at several identities, some in difference formulas, some in product formulas, looked at several identities that are useful in solving trig equations and simplifying expressions, proving other identities. In this section, we're going to look at some additional identities that are helpful in doing this. All right, we'll start with the double angle identities. The first one, the sine of 2 alpha is equal to 2 times the sine of alpha times the cosine of alpha. That's the sine double angle identity. And then the cosine has 3 versions. The cosine of 2 alpha, it could either be cosine squared alpha minus sine squared alpha, 1 minus 2 sine squared alpha, or 2 cosine squared alpha minus 1. We can use any one of these 3 versions of this formula depending on what we're trying to accomplish. All right, let's look at some examples. All right, with this example, we're going to find the exact value without solving. We're going to find the exact value of the sine, cosine, and tangent of 2 times an angle without actually solving for the angle itself. All right, since we're looking for an exact value, the calculator is probably not going to be that helpful to us, right? We don't want a decimal approximation. All right, so to find the sine of 2x, we'll use the double angle identity for the sine, which says that the sine of 2x can be rewritten as 2 times the sine of x times the cosine of x. All right. Well, let's see. We know the cosine of x, but we don't know the sine of x. Is there a way that we can determine what the sine of x is? Well, recall the Pythagorean identity. The sine squared of x plus the cosine squared of x equals 1. We can use this Pythagorean identity to find the sine of x, since we know the cosine of x. Right? So we can say then that the sine squared of x plus, since the cosine is 2/3, plus 2/3 squared would be equal to 1. All right? So sine squared of x plus 4/9 equals 1. And subtract that 4/9 from both sides. So sine squared of x then is 9/9 minus 4/9, or 5/9. So sine of x then would be the square root of 5/9, or we could say that's the square root of 5 over 3, right? Since the square root of 9 is 3. All right, well, the Pythagorean identity was helpful for us to find the sine. Now we can write the exact value of the sine of 2x because we now know the cosine of x and the sine of x. All right? So the exact value here is going to be 2 times, and our sine was square root of 5 over 3. Our cosine is 2/3, right? So 2 times 2 times the square root of 5 is 4. Square roots of 5 over 3 times 3, 9. Right? So there's our exact value of the sine of 2x. All right, what about the cosine of 2x? For the cosine, we have several options, don't we? Like we could use any one of these angles. It doesn't matter, or any one of these, equation formulas. It doesn't matter which one we use since we now know both the sine and the cosine. But I think I'll just use the version that only requires knowing the cosine since that's the given, just in case I made a mistake with the sine, right? So the cosine of 2x could be rewritten. We're going to use the version that only includes the cosine. Cosine squared, 2 times cosine squared of x minus 1. Right? We know the cosine. It was given. It was 2/3. So the exact value here is going to be 2 times 2/3 squared minus 1. Right? So what is that? 2 times 4/9, or 8/9 minus 1. It could be written as 9/9. So the cosine of 2x is going to be negative 1/9. All right. Tangent, well, We actually do have a double angle identity for the tangent, but it requires us to know what the tangent is. We could use the double angle identity and find the tangent first, or you know what's easier, since we know the tangent identity, it says that it's equivalent to the sine over the cosine, we could rewrite this as the sine of 2x over the cosine of 2x, right? And we know those values now, don't we? The sine of 2x is 4 square roots of 5 over 9. And the cosine of 2x is negative 1/9, right? So when we simplify this, the tangent of 2x is going to be negative 4 square roots of 5. Okay, so the double angle identities is a couple basic situations. We can use them to find exact values. We can also use them to solve trig equations. All right, so let's look at some equations here. In the first one, we have 2 times the sine of 2t plus 3 times the cosine of t equal to 0. All right, we're going to look for all the solutions over the interval 0 to 2 pi. All right, so that's once around the unit circle. Okay, so now the problem with solving this equation actually is twofold, right? Look, one problem here is that I have different arguments. Another problem is I have different trig functions, right? So I think that the first thing that I need to do here is I need to get all the trig functions having all the same argument, right? Having all the same argument. So let's begin by using the double angle formula for the sine. I can write it up here so we have it. The sine of 2t is equal to 2 sine t cosine t. Oops, that's the way they wrote it. Erase. There we go. 2 sine t cosine t. All right, so we'll make that substitution here. Okay, and what we're substituting, we're just going to substitute, let's see, for the sine of 2t. And the whole thing we need to substitute is 2 times the sine t times the cosine t. All right, so all we're substituting is this part here. So we want to make sure that we don't lose that additional 2. Okay, so we'll make that substitution. Then this will be 2 times 2 times the sine of t times the cosine of t plus 3 times the cosine of t equals 0. All right, well, 2 times 2 is just 4. All right, so let's rewrite that. 4 sine t times cosine t plus 3 cosine t. All right, now since this is equal to 0, the zero product principle might be helpful here, right? Look, I could factor out a cosine of t, right? Let's try that. So I'll factor out the cosine of t. What's left? 4 times the sine of t plus 3. Okay, that still equals 0. Now I can employ the zero product principle to solve this equation. I have 2 factors, so either the cosine of t equals 0 or 4 times the sine of t equals 0. All right, well, for the cosine of t equals 0, that's a known value on the unit circle, right? The cosine is 0 when the x-coordinate of the terminal point is 0. So we see that happening in 2 places. We see that at pi over 2 and 3 pi over 2. All right, so there's 2 answers. But now we have to solve this other factor. Oops, I left something off there, didn't I? That's 4 times the sine of t plus 3 equals 0. There we go. All right, so solving here, let me solve for the trig function. So I'll subtract 3 and divide by 4. So the sine of t then is going to be negative 3/4. And that is not a known value on the unit circle, so we'll have to find that value with the calculator. All right, take the inverse sine of both sides. So t then is going to be the inverse sine of negative 3/4. Let's see what that value is. Calculator's frozen. There we go. Inverse sine of negative 3/4. And we have negative 0.8481. Okay, we have a little bit of a problem though, because look, our interval was supposed to be 0 to 2 pi. But when we use inverse sine, we know that we're restricted to quadrants 1 and 4, right, with the restricted domain. So where are we here? Let's see. Take a look at this on the unit circle. All right, negative 0.84, we'll just say it's there, right? Negative 0.8481. We need a positive version of that same angle, right? The positive version would be here. So it looks like that's going to be 2 pi minus 0.8481, right? See that? Because you go all the way around to 2 pi, then come back by that same amount. All right, so the actual value that we want to report here is the positive version, so at 2 pi minus 0.8481. Okay, 3 solutions. All right, let's look at this next equation. The cosine of 2t equals the sine of t. All right, so similar situation here. We have different arguments. We also have different trig functions, which could be a problem. But for now, let's start by rewriting this equation so that all terms have the same argument. All right, so we're going to need to use one of the cosine of 2t identities, right? One of the double angle cosine identities. Well, which one should we use? We could use any one of these 3 and probably come to a solution. But since I have a sine and only a sine in the equation with the cosine of 2 times the angle, I think I'm going to use this middle version because it might be the easiest thing to solve. All right. So let's make that substitution. We're going to use this one. The cosine of 2t equal to 1 minus 2 times the sine. Oh, it's sine squared, actually, of t. 1 minus 2 sine squared t. All right, so we'll make that substitution. So this guy is going in here for this guy. We now have 1 minus 2 times sine squared t equal to sine t. All right, that just turned quadratic on us. Look at that. So that means I want to set it equal to 0 to solve, right? I'll move everything over to the right. So 0 then equals 2 times sine squared of t plus sine of t minus 1. And that'll factor into 2 sine t minus 1 times sine t plus 1. Is that right? Negative 1, we got negative sine of positive. Yeah. All right, so now I can use the zero product principle, right? And I'll go up here to finish. We'll say 2 times the sine of t minus 1 equals 0, or the sine of t plus 1 equals 0. All right, solving the first equation, we'll add 1 and divide by 2. So the sine of t is 1/2. That's a known value from the unit circle. So let's see what angle gives us a sine of 1/2. We go back and look. Sine, that's our y coordinate. There's 1. The sine is 1/2. Where else? Y. Here's another one where the sine is 1/2. So it's pi over 6 and 5 pi over 6. 2 solutions there. All right, now to solve this equation, we just subtract 1 from both sides. So the sine of t equals negative 1. That's also a known value on the unit circle. All right, so let's just look. Where's the sine negative 1? Down here at 3 pi over 2, the only place. Okay, so our third solution here then is going to be 3 pi over 2. Okay, 3 solutions for this one as well. One more. Let's look at one more. See if I can make myself a little more room, right. 8 times the cosine of 2 alpha equals 8 cosine squared of alpha minus 1. Okay, my problem again, I got this double angle identity. I need to express that as I need that argument to be all the same. So I need it to be just alpha. All right. So which double angle identity do I want to use? I probably could solve it with this identity, but it doesn't look good. That's introducing a sine when I already only have cosines. So let's look at them. How about if I use, I don't know which one, but let's try this version of it because it only involves cosines. Okay. And that may make this easier to solve. If it doesn't, maybe we'll go back and try one of the others. All right, so the version we're going to use this time, cosine of 2t equals 2 cosine squared of t, 2 cosine squared t minus 1. All right, so we'll make that substitution. We're going to put this in for this down here. Okay, I don't want to lose my 8. I've got to be careful with that when I make this substitution. So let's 8, that's going to be 8 times what? 8 times 2 cosine squared of t minus 1. I make that substitution, and then that'll be equal to 8 cosine squared. Oh, we're not t anymore. They switched us to alpha. Switched to alpha. All right, let's do alpha. 8 cosine squared alpha minus 1. All right, simplify. Let's just multiply out that 8. We have 16 cosine squared alpha minus 1 equals 8 cosine squared alpha minus 1. Let's see, let's combine the like terms. I think I'll put the cosine squareds over on the left. So we'll subtract 8 cosine squared from both sides. And we'll have 8 cosine squared alpha on the left. And then we'll add another mistake. Look, we distribute that 8, that's 16. 8 times negative 1 is 8. There we go. Then we'll add that 8 to both sides, right? So 8 minus 1 is 7. Okay, now to solve for that trig function, let's divide both sides by 8. So the cosine squared of alpha then is 7/8. And then we'll need to take the square root of both sides. Kind of out of room, so let's come up here. So the cosine of alpha then is going to be the square root of 7/8. All right, but we want alpha, right? We don't want cosine of alpha. So we'll use our inverse function here. Alpha then is going to be inverse cosine of square root of 7/8. Okay. Now, do we want a positive or negative here? I think we do, because we're solving for a variable, right? Let's see what we get. Come back to that. All right, so inverse cosine. Let's see, inverse cosine of the square root of 7 divided by 8. Okay, and there's our answer, 0.3614. All right, do we have, yeah, we do. We do have other values here, don't we? Let's find it. We got one more. Let's find it. Let's make a unit circle and find it. All right, so the first angle is here. That's our 0.3614, right? And the cosine at that angle is square root of 7/8 with some y, okay? Where do we have one with the same cosine? Down here. Okay, this one has the same cosine, square root of 7/8. The y is going to be negative. Okay, and we want to stay in our interval 0 to 2 pi. So the angle that we want here is this guy. So it's going to be all the way around to 2 pi and then back a little bit, right? So one angle here is 0.3614, call it alpha sub 1. We have another one, though, call it alpha sub 2. It's going to be 2 pi minus 0.3614. Okay? Two solutions. All right. So these double angle formulas can also be valuable in proving identities. Let's look at a few of these. All right, so here we're going to prove the identity that the sine t minus cosine t, all of that squared, is equal to 1 minus sine of 2t. Okay, well, recall that when we're proving an identity, we only want to work on one side of the equation. So we need to choose a side to work on. I think I'll choose to start on the left-hand side. All right, and I think what I want to do first is just multiply this out. Let's just simplify it and look at it. All right, so we'll have the sine t minus the cosine t times sine t minus cosine t. All right, that's on the left-hand side, so let's multiply it out. First times first, so it'll be sine squared of t, right? And then we have a negative sine t cosine t and another negative sine t cosine t, right? So that'll be minus 2 sine t cosine t. And then cosine t times negative cosine t times negative cosine t is going to be positive cosine squared of t. All right, so I can now add this sine squared and cosine. I can rearrange things. Look, usually what I do when I'm proving an identity at this point is I think about where I'm headed, right? I think about where I'm headed. And I see I'm going to need a double angle. What is that formula again? The double angle formula is equal to 2, for sine anyway, is equal to 2 times the sine of t times the cosine of t, right? And so I'm headed towards that. I need this over here so I could substitute it in for sine 2t. And look at, I've got it right in the middle there. Okay. When I notice that, then what comes to mind is the Pythagorean identity. Look, if I rearrange these, I could write this as sine squared t plus cosine squared t minus 2 times the sine t cosine t, right? And look, sine squared plus cosine squared by the Pythagorean identity, it's equal to 1, right? Pythagorean identity. So I can make that substitution, and now I have 1 minus 2 sine t cosine t, right? And 2 sine t cosine t is an identity for the sine of 2t, right? So I can make that last substitution. Here's my reason over here. The sine of 2t equals 2 sine t cosine t, right? With my t's on there. So now I can make that substitution and we have our proof. 1 minus the sine of 2t. Okay, let's look at another one. Oh, this one's interesting. We've just got tangents and cotangents, right? I've got a problem here though. Look, I've got a double angle that I'm going to need to be a single angle. All right. So, but I don't really have a cotangent double angle identity, do I? All right. So if I'm thinking about where I want to head, right, I'm not working on this side. I'm just going to make a little note to think about where I want to head. I want to work on the left-hand side. But where do I want to go? Well, let's see. I have double angle identities for sine and cosine. So, I could make a note that the cotangent, or x now, the cotangent of 2x is equal to the cosine of 2x over the sine of 2x, isn't it? And the cosine of 2x, well, that has all kinds of identities that could be used. I'm not sure which one I'm going to need. There's only one for the sine of 2x, and that's 2 times the sine of x times the cosine of x. This could be something, I don't know. So this is what I do when I'm working on an identity. I kind of think about where I'm headed. Okay? Now, let me go back and work on the left-hand side. All right, I want to get rid of cotangents and tangents. I want to work in terms of sine and cosine because that's what I've got double angle identities for. So let's rewrite this. Let's rewrite the cotangent of x as the cosine of x over the sine of x, right? And then we'll rewrite the tangent as the sine of x over the cosine of x, right? So, oops. So the only thing that we've done here is, we'll put a reason for what we've done there. What we've done is use the cotangent identity. Cotangent equals cosine over sine. And we've used the tangent identity. Tangent equals sine over cosine. Okay. All right. Now I'm looking at where I want to go. I know what I want my denominator to be, 2 sine x cosine x. Well, so I think, and I only want one term on the right-hand side, so I'm going to have to combine these terms. To combine them, they're going to need a common denominator. So I'll multiply the first term by, and I'm going to use cosine x over cosine x because I know that I need a sine x cosine x in the denominator. Okay, so then I multiply that second term by sine x over sine x. All right, so now what do I have? I now have cosine squared x minus sine squared x over cosine x times sine x. All right, why can I do this? I'll just say the reason is that I can simplify. I'm simplifying and adding fractions. Okay, since it's a proof, I want to make sure I identify the reasons why I'm taking these steps, right? Okay, now what do I do here? Well, let's see. I need to get to something. I need something up in the numerator. This is cosine squared minus sine squared x. All right, let me look at some of my cosine 2x, my double angle identities for the cosine. Let's go back and look at those. Look at this one here. This might be very helpful to us. Cosine squared minus sine squared. What am I seeing here? Cosine squared minus sine squared. I think I might have gotten to a point where I can do a substitution, right? So I think the version that I want to use here is that one. That is a cosine 2x. So I can make that substitution, and I get a cosine 2x in the numerator, right? And my reason here would be because cosine 2x equals cosine squared x minus sine squared x. Right, that's my reason to make that step. Now my denominator, it's cosine x sine x, right? But I want it to be 2 cosine x sine x, or 2 sine x cosine x, right? I want a 2 down there so that I can make the substitution. Well, I can add a 2 if I'd like, but I need to undo it as well. See what I'm doing here? I can add that 2 so that I can make that substitution. So I want to substitute that for that. So, and I didn't have the 2, so I have to add the 2. But then I have to undo the 2 as well because I don't want to change the value of that denominator. Right? Okay, so I can make my substitution now. Sine of 2x is equal to 2 cosine x sine x, or 2 sine x cosine x. That's the same thing, right? Multiplication is commutative, so it doesn't really matter. All right, so we'll make that substitution. So then we have, let me copy that numerator, cosine 2x over 1/2 times the sine of 2x. All right, now I got this weird business of this 1/2 down in the denominator. So let's simplify that. This is like 1 cosine 2x divided by 1/2 sine 2x. 1 divided by 1/2, of course, is 2, right? So this can become 2 cosine 2x, right, over the sine of 2x, right? And that's just a simplified situation. All right, now look at this. I got a cosine 2x over sine of 2x. I can make the substitution that I need because the cotangent of 2x is equal to the cosine over the sine. And I've just proven my identity. Okay? Let's do one more. All right, prove, oh, this is a good one. Cosine of 3x equals cosine cubed x minus 3 sine squared x times the cosine of x. Well, a triple angle. I don't have any triple angle identities, right? I only have double angle identities. I do, however, have some indifference identities, don't I? Recall that the cosine of alpha plus beta from the 7.2 lesson, the cosine of alpha plus beta is equal to the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. All right, so I could rewrite the cosine of 3x as the cosine of 2x plus x, right? 2x then could be considered my alpha, and x could be considered my beta. Okay? So let's rewrite that. All right, so this would then become the cosine of 2x, so that's my alpha, times the cosine of x minus the sine of 2x times the sine of x. Okay, my reason here again, I'm just doing this substitution. Cosine of alpha plus beta is equal to cosine alpha, cosine beta minus sine alpha, sine beta. Okay, now I can use a double angle identity here, right? So which double angle identities? I don't know about the cosine. Let me leave that one alone again because I have, for now, because I have too many options. Let me just make my sine substitution. We know that the sine of 2x is equal to 2 times the sine of x times the cosine of x, right, with that identity. So let's make that substitution. All right, so this now becomes minus, and here's what we're substituting. This gets substituted in for this. All right, so minus 2 times the sine of x times the cosine of x, times the sine of x. I got one more that I need to bring down, right? Sine of 2x was this, but I still had that one more sine of x. Okay, all right. Now I got to think about, what do I want to do? Which version of the double angle for cosine do I want to use? What do I think would be the easiest? I could probably make it happen with any of them, but what would be easier? Well, what do I need to get to? Let's see. Let's look over there. I need a cosine cubed, right? Here, this is a sine squared. This is 2 sine squared cosine x. I need 3. I need another sine cosine x. So which one do I want to use? Geez, I don't know. So I'm going to just try one and see. It seems to me like maybe this might work, and if it doesn't, we'll just erase it and go a different path. I think that I want to introduce another sign because I need sine. No, I don't want to introduce another sign. Oh yeah, no, I do. Cosine squared. 2 sine squared. Let's try this one first. If it doesn't work, we'll come back and try another. I'm going to use the cosine version. Nope. Yeah, let's try and see. 2 cosine squared x minus 1. I don't think this is going to work, but let's try it and see. All right, so I'm going to make, here's the substitution that I'm making. Oh, look at all my colors. Look at awesome. I want to try making this substitution for this and see if I can make this happen. I don't think it's going to. I think I'm going to have to back up and try something else. Let's see. All right, so 2 cosine squared x minus 1 times the cosine of x. Well, maybe it will work. Okay, then minus 2, and the sine times the sine is sine squared, so I'll do 2 sine squared and cosine x. Now, this version is almost getting us where we need to be, but not quite. So let's back up and let's try something else. Let's try, I need a sign in there. So let's try this other version here. Let's try cosine 2x is equal to cosine squared x minus sine squared x. Let's make that substitution. All right, so now this guy is getting substituted in for that guy. All right, so cosine squared x minus sine squared x times cosine x. This is looking better. All right, so now let's just simplify by distributing that cosine x. So we'll have cosine cubed x minus sine squared x times cosine x, and then minus 2 sine squared x cosine x. All right, so I made that substitution. Now let's just simplify. I think we're going to have what we want. Look, this is minus 1 sine squared cosine squared, or cosine, minus 2 sine squared cosine. When I combine those, I have cosine cubed x minus 3 sine squared x cosine x. All right, and now I've proved it. Okay, so a couple more things in here. Half angle and power reduction identities can be useful. I don't like these half angle identities. I don't use them very often, but they can be very helpful. Power reduction identities as well. Sometimes you want to rewrite a single angle as a double angle, or you may have a pattern where you can undo a double angle to a single angle and squared. Let's take a look at some examples using these half angle identities to find an exact value. All right, so if the secant of x is 4 and x is in between 270 and 360 degrees, that means x is in quadrant 4. All right, x is in quadrant 4. We want to find the exact values for these sine, cosine, and tangent of half angles without solving for the angle. All right, we have a formula for the sine of x over 2, the half angle. There it is. It's going to be plus or minus the square root of 1 minus the cosine of x over 2. Okay? Now, let's think about that. Plus or minus, do I want the positive or do I want the negative? Well, if x is in quadrant 3, let's think about this for a minute. 4, I'm sorry. If x is over here in quadrant 4, this angle is in quadrant 4, right? So that guy all the way around there, that's our angle x. Half of that angle is going to have to be in which quadrant? It's going to have to be up here in quadrant 2. Right? Any angle here that you cut in half is going to lie somewhere up here in quadrant 2. So this is important because this tells us something about the sine and the cosine, right? This tells us that the sine is positive, right, up here in quadrant 2, and the cosine is negative. All right, so if we want to find the sine of alpha over 2, we don't care about the negative, right? All we care about is the positive. So this is all we care about. We don't care about the negative. All right, well, to find this exact value, we need to know what the cosine is, and we don't. We only know the secant. But we do have an identity, right, that tells us that the secant of an angle is 1 over the cosine, all right? So then rearranging things, we could say that the cosine is 1 over the secant, right? And since the secant is 4, we know that the cosine of this angle is 1/4. All right. Now, but we're over here in, and we're fine. We're in quadrant 4 where it's positive, and that's B. All All right, so now we can just plug that value in and we can calculate the sine of x over 2. It's going to be the square root of 1 minus 1/4 over 2, right? Positive only, right? Or we could say that's positive the square root of 1 minus 1/4, that's 3/4 over 2, which of course is the square root of 3/8. Positive square root of 3/8. Okay? Now how about the cosine? All right, well, the cosine has its formula as well. There's our cosine formula. So let's copy that down. It's going to be plus or minus the square root of 1 plus cosine over 2. All right. Is it positive or negative? Okay, well, we're in quadrant 2, so it's going to be negative. All right. So this time, we want the negative version of it. So it's going to be negative square root of 1 plus 1/4 over 2, which is negative square root of 5/4 over 2, or 5/8. All right, so here's our sine, he's positive. Here's our cosine, he's negative. And that makes sense because we're over in quadrant 2. Now, for the tangent, I mean, there is a half angle identity that I could use, or I could just say it's the sine over the cosine, right? We'll practice the identity. The identity says the tangent of x over 2 is 1 minus the cosine of x over the sine of x, right? So what's that going to be? 1 minus 1/4 over, oh wait, we have a problem, don't we? We don't know the sine. Well, we could calculate the sine, couldn't we? But I'm feeling tired and we're at the end of this lecture, so I'm not going to do that. You know what I'm going to do? I know that the tangent is the sine over the cosine. And it's going to be so much easier since I know the sine of x over 2. I don't know the sine of x. Right? The sine of x over 2, we found it over here. It was positive square root of 3/8. Okay? And the cosine we found was negative square root of 5/8. So when we simplify all that, that's negative, put that all into one radical, right? 3/8 over 5/8, which is simply negative root of 3/5. Okay? So that's it. That ends the lecture. Oops. That ends the lecture. That ends the lecture for section 7.3.